My name is Mike Abrams for Georgia Tech's Introduction to Cyber Physical System Security class, Spring 2019. I would like to talk to you about FlowFence, practical data protection for emerging Internet of Things application frameworks. The authors of the paper, Erlance Fernandez, Justin Palpor, Amir Rahmati, and Atul Prakash, were students of the University of Michigan, and Danielle Simeonato and Mauro Conti from the University of Padova also contributed to the research. Their presentation to the USENIX Security Symposium was in August 2016. A few of the items that I would like to discuss are an overview and present vulnerabilities, the problem statement, the solution, a high-level view of FlowFence, the concept of sandboxes as it relates to this solution, a high-level view of the architecture, how with this solution leaks are prevented in IoT applications, the concept of taint tracking, key value store and event channels, and we'll conclude by discussing the results along with closing comments. The Internet of Things, or IoT ecosystem, is composed of data-producing and consuming devices, typically privacy-sensitive, that optionally actuate physical devices. Emerging IoT programming frameworks have many application domains that enable developers to build applications that compute on sensitive data produced by smart homes and wearables. Today's IoT framework only have permission-based controls. Frameworks control what data an application can access. Existing frameworks do not control how those applications use the data once they have access. This method is inadequate, as evidenced from the growing reports of data stealing malware in the smartphone and browser extension spaces. Users have no choice but to take it on faith that an application will not abuse its permissions. The problem statement that Erlance Fernandez and his colleagues sought out to solve was, how can we enable applications to compute on sensitive data, and they use an example of data that IoT generates, while mitigating data abuse. A solution is needed that will force applications to make their data use pattern explicit, and then enforce the declared information flows, while preventing all other flows. Well, introducing FlowFence. It enables robust and efficient flow between sources and sinks in IoT applications. A source is defined as any originator of IoT events. A sink, conversely, is a class or function designed to receive incoming events from another object or function. FlowFence addresses the need to not have a special purpose language. It avoids implicit flows, does not require instruction-level information flow control. It supports IoT app flow policy rules and IoT diverse app flows involving a variety of data sources. At a high level, FlowFence creates a data flow graph at runtime. There is a label-based flow control, allowing for component-level information tracking. Flow enforcement is through label policies. FlowFence also incorporates language-based flow control, restructuring apps to obey flow rules, where the developer declares the flows. Also allows for flow support of diverse publishers and consumers of data, use of existing operating systems, languages, in tools. Here's an example of a data flow graph that explicitly maps out what each application can and cannot access. This example is from the Face Door application, and you can see each aspect of the application, the camera and door status in this case, has its own unique flow. Sensitive data is available only to functions executed within each application's sandbox. Developers must identify those functions to FlowFence. This is accomplished by encapsulating functions operating on sensitive data in Java classes and then registering them with the FlowFence infrastructure. FlowFence treats functions operating in the sandbox like a black box. Shown in the lower left of the screen is a typical IoT framework where there are high-level permissions that may or may not include a whitelist of approved applications. Two main components of the FlowFence architecture are a series of sandboxes that execute untrusted, app-provided quarantine modules in an isolated environment, preventing unwanted communication. The second component is a trusted service that maintains handles and the data that they represent. The trusted service uses operating system support to create sandbox processes that FlowFence uses to create quarantine modules. A quarantine module is essentially a developer-written code that manipulates sensitive data. When a quarantine module arrives for execution, FlowFence reserves a sandbox for use only by that quarantine module until execution completes. Once a quarantine module finishes executing, FlowFence sanitizes that sandbox to prevent data leaks by destroying and recreating the process. FlowFence creates sandboxes with an isolated process flag set, which causes the OS, in this case Android, to activate a combination of restrictive user IDs, IPC limitations, and strict policies. These restrictions have the effect of preventing the isolated process from communicating with the outside world except through an IPC interface connected to the trusted service. Attempts to declassify data using the non-trusted APIs are denied. FlowFence provides security guarantees in two ways. First, quarantine modules are essentially internal functions, developer-written code modules that compute on sensitive data that run in a sensitive or system-provided sandbox. Each application is split into two parts, sensitive and non-sensitive code, and developers can chain together multiple QMs to attain useful work. Secondly, we have opaque handles. Opaque handles have a hidden reference to the raw sensitive data associated with a taint set or label and enforce flow control that monitors data flows through programs. Flow policies are enforced in a publisher application when those policies are associated, in the example of the connected home, with one-to-many sensors. Taint labels are added to its data where the tuples are of the form app-ID, name, where an app-ID is the identifier of the publisher app and the name is the name of the taint label. A flow rule is of the form taint label. Taint tracking permits sensitive data to be made available to apps only through functions submitted for execution in provided sandboxes. When a function wants to declassify data, it uses the provided trusted APIs that check flow policies before declassifying the data. Upon function execution completion, return data is converted to an opaque handle before returning control to the non-sensitive application code. Outside the sandbox, the handle does not reveal any sensitive data information. Flexible key-value stores is one of the primary ways data is shared between publishers of tainted system or sensitive data and consumer applications operating in a device-agnostic way with customers only having to know the type of data, or taint label, they are interested in processing. Each application receives its own key value store, and it can update the value associated with the key by storing the key, the sensitive value, taint, and then the label, while executing a quarantine module. Event channels support the design pattern in registering callbacks for IoT device state changes. An app creates that channel statically by declaring them in the manifest file. The team ported 3 Internet of Things applications to FlowFence: the Smart Home API, the Google Fit API, and the Android Sensor API. Memory overhead, quarantine module call latency, and serialization overhead were studied. In addition, security aspects, developer effort, essentially what it took to refactor the application to run within FlowFence architecture, and end-to-end latency were studied. Here we have a main program that calls a module to compute feature vectors. It accesses an IP camera, computes features, and sends data back to the main program. The main program takes the features as input and accesses the state of the door. Assuming the face is authorized, the door is unlocked. The program then updates the internet website. Can you tell what flows might be useful to secure the application? Well, the answer might be on the next slide. What you see here is the refactored application where the main program calls a module to compute features that is in the quarantine module running in a sandbox. This module will access sensitive data. The DC refers to the data of the camera. TC is the taint label of the camera data. QM features returns an opaque handle which refers to the transformation of the input data. The only thing that the main program can do with the opaque handle data is to send it to another quarantine module. So it sends it to a recognizer QM. This QM also accesses the door state data. The taint label reflects that it has accessed the camera and the door state data. Assuming the face is recognized, it will try to do a declassification of the door controller using one of the FlowFence APIs. Before the process is allowed to proceed, the taint labels are read from the caller and the flow policies are analyzed. These are shown in red. These policies state that the camera and the door state data flow through the controller, and so the request will be able to go through. There is also another quarantine module report that reads the door status and declassifies that through the internet, along with the corresponding flow policy. This app could try to leak the opaque handle, but it is of no value since the data is not sensitive. Also, the application could try to leak the data to the internet, but there is no policy that allows this flow, so that action will be denied. An opaque handle is associated with applicable taint labels. Each taint label has an app ID and a label name. The policy is simply a set of flow rules. A flow rule is of the form taint label which flows to a sink. We show 2 flow rules here: the camera data to the UI, shown under example policy, and the heart rate data going to the internet. The key value store functions as a data sharing mechanism between publishers and consumers of data. Let's look at an example. QM1 in this case has some sensitive data, T1. When QM1, the key, wants to publish data, it simply writes the data, specifying the name of the key, into the key value store as well as the taint label. Later on, QM2 can read the data, specifying the name of the key, since it is public, inheriting the taint value label, and receives the data in return. To ensure that the key is not corrupted, it is created outside of the QM to prevent publishers and consumers from taint stripping. As we look at the results of porting of the three applications into FlowFence's architecture, several items are noteworthy. From a computation and memory overhead perspective, the per sandbox memory overhead was around 2.7 megabytes, and the QM call latency was roughly 92 milliseconds. From a smart light perspective, it was refactored with under 80 lines of code, but showed a data security risk, potentially leaking location in one area of the program. The Face Door application was refactored with roughly 130 lines of code, but had the potential to leak images of people from the camera to the lock, from the door state to the lock, and lastly from the door state to the internet. The heart rate monitor app was updated with just under 100 lines of code, but showed it could leak images and a person's heart rate between the camera and the UI. The overall performance of the reported applications, we see that the enroll latency of Face Door, defined as from the time the app is given a bitmap until the time the app computes the feature vectors, was 100 milliseconds. The recognition latency, basically the time the program is given feature vectors until it matches data in a database, was an increase of a reasonable factor in terms of latency. End-to-end latency was defined as the time that a location beacon enters the fence until the time the light was turned off, a roughly 100 millisecond delay. There was a slight decrease in throughput within the heart rate application, but this did not impact the application from computing the heartbeat of the user. There are some limitations of the existing design, including the existing applications must be refactored in order to run in FlowFence. There is no limitation that requires IoT applications to run in the cloud, and in fact, FlowFence is a hub-first architecture rather than a cloud-first architecture. Side channels was noted as a limitation. Attackers can encode sensitive data and data values prior to the time that it takes quarantine modules to return. Techniques equate to leaking low bandwidth data. Their get well plan was that they were going to investigate techniques to restrict particular channels by making quarantine modules return immediately and have them execute asynchronously. Regarding security decisions, the team noted that the solution could not prevent the user from making bad security decisions, and that flow prompts are not explicitly done in FlowFence. Emerging IoT application frameworks only support permission-based access control, and malicious apps can steal sensitive data. FlowFence embeds control data flows within an application structure. FlowFence is a set of communication and communicating quarantine modules communicating via opaque handles, taint-tracked opaque references to data. Non-sensitive code orchestrates QM execution. FlowFence supports policies that enable secure IoT applications. The authors ported 3 IoT apps in 5 days, each requiring less than 140 lines of code. Performance testing revealed FlowFence had an overhead of roughly 4.9% latency over those non-secure applications. Face-to-face recognition to unlock a door as an example. FlowFence is the first security model focused on controlling data flows in the IoT space. FlowFence introduces the opacified computation model, requiring consumers of sensitive data to explicitly declare intended data flows. FlowFence enforces declared flows and prevents all other flows, ensuring a secure environment. Thank you.